All right, it's 11:15. We'll get going. So make sure you look at your homework. Make sure you ask questions. We're going to cover material today and Friday through note set 4 that will cover all of the material on the homework. And so make sure you know what you know and what you don't know. Make sure you print out the homework. You're looking at it. Start it early so you're not rushing to finish on Friday night. Don't forget to do PLAs. Look at the syllabus and figure out when the first exam is. That is scheduled. It's in stone. And so put it on your calendar. Make sure you set aside time to do that on Canvas. If you have problems scanning in information or scanning in your homeworks, or there's issues with that on the exam, you can always take a picture of your written part and submit that. That's fine. Sometimes the homeworks are locked for PDF because that's easiest to grade, but on the exam, you can submit a cell phone picture, you can submit whatever you want. Yes? Oh, one was on 2:30. I'll try and make them do midnight the day before. 2:30. Okay. Yeah, you just have to email me, and if one shows up at 2:30, because one time we did PLAs a little bit differently, so that might still be in Canvas. I'll try and kill all those, but usually I'll try and make it midnight the day before. Yeah, yeah. If something looks funny, just shoot me an email. Usually I can fix it quickly. Any other questions? Any questions on the homework? Remember, print this off. You can ask me questions in class. I'll answer them on the video so everyone can see it. And so remember that for before and after class today and during class on Friday. Anything else? All right. So we know polymers are really useful. And there's a lot of polymers that are polluting the environment right now, but there's also a lot of good that polymers do. And one of the interesting things that people have worked on lately is that in Africa, there's a very well-developed primary school system for various reasons, but there's good schools in Africa. However, some of the kids have problems learning because they can't see very well. And so there's not a well-developed eye care infrastructure in Africa. And so it turns out that if you diagnose these problems for kids that can't see the board or can't see a book in front of them, and you give them a pair of glasses to fix their vision, their learning goes way up. And so having access to good glasses, or at least glasses to help kids see, increases learning greatly. And so one of the projects that's been worked on is to use this polymer and make an adjustable lens where you can change the amount of fluid in this flexible polymer bladder and get different types of lenses. And you need different types of lenses for different types of vision problems. So that's good. That's one solution. You can make a bunch of these and send them over to Africa. But if you're asking kids to wear glasses that look like this, kids are interested in fashion and looking good to their peers, and they don't want to wear these funny looking things. And so one of the things that people have done, it turns out that this is now a resource all over the world. So plastic water bottles, there's bottled water all over the world. There's lots of PET or polyethylene terephthalate plastic water bottles. You can recycle that. You can turn it into 3D printing feedstock. And now you have a source of plastic where you can start to 3D print new glasses, or you can 3D print glass frames. And it turns out you can get lenses without too much difficulty. But they've started to give kids opportunities to 3D print their own glasses in schools in Africa and work on 3D printing, and they love it. You get to design your own glasses. You don't have to wear these adjustable things. It starts to become a fashion statement rather than a detriment to looking cool. And so this is one of the good things that plastic has done. Now you can build your own printers out of whatever e-waste is around, and you can start to give glasses that are 3D printed to school kids in Africa to increase their learning. So this is something to remember, and this is why polymers are useful. And if you know a lot about PET, which we're going to talk about in a second, and you know its thermal properties, its TG, all that stuff that we're going to talk about, you can participate in this really good thing. All right, I just wanted to share that story. Okay, so we're making polymers now. We want to go from monomer. And so when I ask you about where do polymers come from or what small chemicals do you need in order to make a polymer, we start with a monomer and then two monomers connected, dimer, trimer, etc., and eventually a polymer. So key to this is knowing what is a monomer and what functional groups do you need, and then how to represent that as a polymer. And we've already done this for ethylene, making polyethylene. And of course, we can add in all of the hydrogens. I'll try and do that, but there's no guarantee that I'm going to get them all the time because we're going quickly. And so make sure you can go from monomer to polymer, especially for polymers like this. Remember, the generic monomer formula is like this. And this is a carbon-carbon double bond. So you can make polymers with any function or with a lot of functional groups that look like that. This is not a carbonyl group. This is not like carbon double bonded to oxygen or anything like that, or a double oxygen bond or whatever weird stuff. It's a carbon-carbon double bond. That's how we make the types of polymers that we know how to make so far. We won't talk too much about this, but we've discussed branching and other things in the past. We'll learn about this later. And the key for this slide is that homopolymers, in general, all repeat units are exactly the same. So it's a single chemistry, and we'll talk about that. And then we have various sorts of copolymers where we have different chemical units, as denoted by this green and these blue spheres. And we can have different flavors of copolymers. We'll come back to that, but you'll see homopolymer and copolymer in the homework. And so you want to be familiar with that. One single chemical unit or two different chemical units that we draw parentheses around. We've also looked a little bit at what polymers look like in terms of their skeletal structures. So we have linear polymers, branch polymers, and then cross-linked polymers. And usually when we talk about cross-linked or network polymers, we'll talk about covalent cross-links. Although there can be ionically cross-linked polymers where you have a metal ion that cross-links two chains. You can have physical cross-links from crystallinity. So there's not only covalent cross-links, but when we draw a skeletal structure that looks like this and we have lines crossing one another, that denotes some sort of cross-link. And usually we'll talk about covalent cross-linking. And this is important because thermoplastics, and if we look at the root of thermoplastics, so this is heat, and the magic of thermoplastics is that they're polymers that can be formed with heat. So injection molding, compression molding, vacuum forming, 3D printing that we just talked about, those are all thermoplastics because you apply heat, the polymer gets soft, and you can shape it. When we have a thermoset, it means that it's resistant to heat. And that's because of these crosslinks. So because those chains are crossing together, you can't form thermosets with heat. They're made a different way that we'll talk about. It's like a epoxy that you buy from the hardware store is a thermoset. It goes from liquid to solid without any heat application if you just buy regular 5-minute epoxy. But it's cross-linked. So if you try and heat up that epoxy and reform it, it doesn't work. It's set, it's resistant to heat. And so that's the general division between linear and branch polymers that are thermoplastics and then thermosets that are covalently cross-linked. Elastomers can be either a thermoset or a thermoplastic. So there's something called thermoplastic elastomers. Rubbers that are vulcanized are thermosets because they're cross-linked with sulfur. And all elastomers are elastic polymers. And so just because we have the three classifications here, elastomers can belong to either one. And so this helps us understand what different polymer objects look like. So this drink cup is a thermoplastic because it was formed using some sort of molding operation. You can see really cool YouTube videos for blow molding bottles or making garbage bags. And so anything that we do extrusion with is usually a thermoplastic. Elastomer, so you can heat up a rubber band, it never flows. If you heat up this cup, it will, eventually slump and melt, so to speak, or get a lot softer. Elastomers are already soft, but you can't heat that thing up and reform it. It's covalently cross-linked. It's not moving anywhere. And then I'll tell you about thermoplastic elastomers eventually. And thermosets, an egg is a fine example. Epoxy is an okay example. You can't thermally reform those. So these are some vocab words that you'll need in your arsenal. Any questions so far? Yes.
So when you say like they can't be reformed, is that like when you heat the epoxy up, for example, would it just not heat up, or would it not go back to like a solidifying kind of way?
Yeah, so epoxy, if you heat it up, it will get warmer. But since those chains are stuck together, in order to get a polymer to flow, you need the chains to move past one another. And they'll only slide past one another if there's no covalent cross links tying them together. So even though this is branched, you heat that molecule up, it'll eventually slide past the other one. This, because everything is cross-linked, those chains won't move very far. And so that's why you can't heat up an epoxy and then reform it using some sort of compression molding or something else, because those chains are stuck and they just won't move.
Okay.
Yeah. You're welcome. Any other questions? Yes.
So when we talk about the glass transition point, how it would be converted, is that related to cross-linking?
So, this is a really good question. So TG exists for all polymers, but TG is softening point for thermoplastics. Thermosets will soften a little bit at TG, but not very much because those chains are stuck together. And so covalent cross-linking is different from TG. TG is a thermal transition. Cross-linking or covalent cross-linking is chemistry. Does that make sense? All right. We'll get into it a little bit more for sure. Any other questions? All right. This is a really important slide. And so everyone's used to a lot of materials having a melting temperature, right? And remember, when you melt something, you go from, oh, sorry about that. You go from a crystal to amorphous. And it's usually a solid crystal, because most crystals are solid, to a liquid amorphous thing. And you can think about water, right? Ice has a crystal structure. You can see it in the X-ray. Water is amorphous. It's got liquid-like structure, which is what we call it in polymers. So the TM is a thermodynamic transition that's first order. So this is first order thermodynamic transition. Steel does this, aluminum does this, ice does this, other small molecules that crystallize do this, wax, for instance, because it's mostly small molecules. But we go from crystal to amorphous. That's a signature of a melting temperature, along with this first order discontinuity that we'll talk about later. TG, you can think of more as a softening temperature, but this is the glass to rubber transition. This is second order. And TG has nothing to do with crystals. And so remember, glass by definition is amorphous. Rubbery materials are going to be still amorphous. So it's an amorphous to amorphous phase transition. That's why it's second order. It doesn't have the same sort of sensible heat that first order thermodynamic transition has, or latent heat, sorry, it doesn't have the same latent heat. But this issue of glass to rubbery, so a hard plastic can be a linear polymer. So we go back to our hard plastics like this cup here, and this cup is composed of linear or branch polymers. But when those molecules are cold, they are all stuck together and they can't move. And so when you're below the glass transition temperature, you're in the glassy state, which means those polymers can't slide past one another because they don't have enough thermal energy to move around. However, when you heat up a glass, we can heat up that window glass there and it will flow. We can heat up this polymer, my cell phone case, which is likely a thermoplastic, it will flow. We put enough thermal energy in those polymer molecules and then they can slide past one another and flow. And so the TG means something distinctly different than a melting temperature. TM has to do with crystals. Not all polymers are crystallizable, but we need some crystals in there. If we have a TM, that's important. And every polymer has a chain structure. And so all polymers are going to have a TG. So for TM, need crystals. And that's not all polymers. And TG has to do with chain motion. Equals all polymers. So even thermosets have little short sections of chains that can start to move around. And so that's why thermosets do have a glass transition temperature, and they would slide past one another, except for the crosslinks, which makes them stuck. So thermosets even have a TG. It's not that useful because you can't push that polymer around, but it does get a little soft. It goes from a really glassy hard epoxy. If you heat up the epoxy, you can probably, poke it with a pin a little bit. It'll feel a little bit rubbery. And so there is a TG for every single polymer molecule. There's not a TM. You need crystals first. All right. Any questions on this? Yes.
So just to clarify, or when sliding past each other, that's when the glass comes to rubber. What if it just happens too fast or too slow? At a rate that it gets cut off.
So the rate of flow is related to the viscosity or the rheology. And so this gets very complicated because you can exchange rate and temperature in something called time temperature superposition, which we won't talk about yet. But let's take this at sort of human timescales or slower timescales. The glass transition temperature is actually defined at 0 frequency or 0 shear. So it's just the polymer's just sitting there. Yeah. But you can change the apparent glass transition temperature of the polymer by speeding things up. Yeah, but that's a different ball of wax. Yes.
Can a polymer have a TM and TG, or is it one of the other?
Yes. So some polymers, and this is a good point. Some polymers that are crystalline are always amorphous plus crystal. Never 100% crystalline. So every polymer has a TG, every single one. And polymers that form crystals have, in addition, a TM. But there's no polymer that's 100% crystalline because you can't get all the polymer chains into a crystal. There's always some defects. Good. Any other questions? Any other comments? Yeah.
So why is semi-crystalline
It has both. And so semi-crystalline polymer will have both a TM and a TG. Yeah. Other questions? Yes.
Will crystalline polymer also always have both?
Yes. Yes. As long as you have crystals, semi-crystalline polymer. A semi-crystalline polymer is composed of a mixture of polymer crystals and the amorphous region. And so it will always have both. Yeah. Other questions? Good. We already talked about that. We already did that. That's fine. All right. So you have a question on monomer repeat unit and molecular weight and things like that. Remember that this is the chemical structure. Remember all the hydrogens on this thing. And so in order to get the right repeat unit molecular weight, you need to take into account all of these guys. And so you can take the repeat unit molecular weight times n, and you get the total chain molecular weight. You have a question on that. And so again, we look for the double bond. And this is a special type of polymerization called addition polymerization. So anytime we talk about addition polymerization, or sometimes we'll call it free radical polymerization or radical polymerization or anything like that, even though you don't need a radical to do addition polymerization. Anytime you have this carbon-carbon double bond, you can open it up just like we've always done, and you can make your polymer structure. And so this unit here is called the repeat unit. So remember, the molecule, the small molecule with the double bond in it, is called the monomer. But once we put that into a polymer and then we go figure out what that polymer is made of, that's called the repeat unit. And so make sure you know the difference between monomer and repeat unit, because they don't have the same chemical structure, right? And you'll be asked to go for simple polymers like polystyrene and polyvinyl chloride and polyethylene. You'll be asked to go backwards and forwards. Sometimes I'll ask you what the polymer is, or I'll ask you what the polymer is given the monomer. Sometimes I'll give you the polymer and ask you what the monomer is. So make sure you can go both directions in this case. So that's called the repeat unit, and N is called degree of polymerization. So what's N for a trimer? Perfect. So as long as you're, we don't call it 100 mer, although you might see that in a homework problem. So 100 mer would have 100 styrene repeat units in it. So N would be 100. And so far, we ignored the N group. So if I don't mention the N group specifically, you can just say, I'm ignoring the N groups. Don't try and make them up. I think in your homework, it tells you to ignore the N groups. There's no guarantee that I'm always going to tell you. But if the problem is not about N groups, you can ignore them. Good. And so remember that the monomer and repeat unit have the same chemical formula, but not the same chemical structure, because we've opened up that double bond, right? But we haven't lost any protons. We haven't lost any small molecules. And so only bonds change, don't lose atoms. And so you can check this easily and make sure that the molecular weight of your monomer is the same as the molecular weight of the repeat unit. Then you haven't lost anything. Make sure all the atoms are there and you haven't messed it up. Questions? Sorry, let me write this down before I answer any questions. Questions on that? And remember, our double bonds can look like this. We can have R groups on them. Usually we have the R groups on one side of the double bond and the other side of the double bond is just protons. We'll talk about why that is later on. But make sure you can do this backwards and forwards. We've talked about polyethylene. We've talked about polystyrene. We've talked about PVC. We've talked about double bond R. You just write those down, practice making those structures. Make sure you get the parentheses and make sure you get the degree of polymerization. If you don't write both of those things down for the polymer and get the bonding right, the answer is wrong. Questions? All right, that's the easy one. Oh, go ahead. What's that? Ah, that's a good question. So remember, as we start, I knew I put this slide in for a reason. As we start with the monomer here, right? You do have to know that this is styrene. It's nice if you have, a little sheet next to you. Okay, I don't really remember what styrene is. Just draw it. Remember the way we form these bonds is you put one electron this way, one electron that way. And so that's going to give you a single bond here and a single bond here. And since it's only one electron, that's why we put the parenthesis through it. Then the end is right here. So the parentheses go right around those carbons that you're going to connect to the next one. So that's how you figure that out. And that's tricky on the homework because the double bond sort of hanging at the carbon-carbon double bonds hanging at a little bit funny of an angle. You're welcome to redraw that monomer to get the orientation right, but don't polymerize through that carbonyl. Don't polymerize through some other funky piece of the molecule. Always think, where is, let's see if we draw vinyl chloride like this. If we always think, okay, the polymer chain is going to go through the double bond like that, then I know where to put my parentheses. Good question. Anything else? Okay, this is the easy one. Make sure you can just do this in your sleep because it's going to get harder on this slide. So before we started class, we did a quick office hours or two. And so this is where your background in organic chemistry and your studying of key functional groups is really going to be helpful. And you don't need to know a lot of these reactions. You just need to know like 4 or 5. And so if you take an amine, this is a big long name, which is hexamethylene diamine. So it's 6 methylene units, which means there's 6 carbons in here. 1, 2, 3, 4, 5, 6. And it's a diamine. So there's an amine on each end. And adipic acid is named using the old school way. You could name it with the IUPAC if you want to, but you just remember that adipic acid has 6 carbons in it. 1, 2, 3, 4, 5, 6. In this case, we count the carbons where the carbonyl is if we're going to make nylon 6,6. Nylon, as you know, is a polyamide. That's a fact that you just have to memorize. And we're going to make amide groups because the polymer is named for the functional unit in the polymer backbone. So we don't call it polyamine acid. We call it a polyamide because that's going to be the new bond or the functional unit in the polymer repeat unit. And so if we take an amine and a carboxylic acid, here's our amine, here's our carboxylic acid, we form an amide, amine, plus carboxylic acid, forms an amide. And since we have 2 functional groups on each of our monomers, so we have amine here and an amine here. So 2 functional groups and we have an acid and an acid here. Again, two functional groups. Effectively, you're going to be able to line up diamine, diacid, diamine, diacid, diamine, diacid. So you're going to build a polymer because all of those groups will react together. And this is the hard part, other than remembering that an amide is a carboxylic acid and an amine. The repeat unit is this big monster right here. So the repeat unit contains both monomers in this polymerization called condensation polymerization. And we call it condensation polymerization because you see this little extra guy right here, water. So when you take primary amine and you react it with the carboxylic acid, you've got H2O is a small molecule that's spit out of the reaction in order to get the polymer connection that you're looking for. So that's tricky. That's a lot more complicated than addition polymerization, but I know you can handle it because it looks so much different, right? No one's going to say, well, I wonder where the double bond was in this polymer, because you really can't just undo one double bond and get it to look like one of those addition monomers. You need to be savvy about what is the functional group. So there's an amide here. There's also an amide here. And then how do I decompose that? And there are some tricks that I'll talk to you about in the next couple of slides. So you're going to have to study this, work with it. You're going to have to draw it out. But the key for the repeat unit is it has to be repeating and it has to incorporate both monomers. And so if you take this repeat unit right here, and I'm going to do that on the next slide. If you take this repeat unit and just draw it out again, okay, I have carbonyl, carbon chain, amide, carbon chain. I have this nitrogen, but that's actually connected back to this carbonyl because the repeat unit, we just slide it over. So here's one repeat unit, slide it over. Here's the next one. Here's the next one. And so you want to make sure that if it's a polyamide, that when you think about where this nitrogen and where this carbonyl go, it's okay that they're on separate sides of the repeat unit because they're going to slide it over and you have an amide anyway. That's confusing unless you go home and practice it and think about it. Questions? Yes? This is a homopolymer. So the repeat unit for condensation polymerizations, well, I mean, this is where it depends. Lots of people will call it a homopolymer. Some people will call nylon 6 a copolymer between adipic acid and hexamethylene diamine. It depends who you're talking to. And so you could say it's a polymer with two monomers in it, then it's very clear, or it's homopolymer nylon 6,6 and there's nothing else in it. But if you say nylon 6,6, everyone knows what that chemical structure is. And I won't ask you the super tricky questions. Most of my homopolymer and copolymer questions will be, it's a homopolymer polystyrene, or it's a copolymer between styrene and vinyl chloride. And then you'll know exactly what's going on. Yes.
So I'm just a little bit confused where the second, like I get that one of the H's and the OH go and make H2O. Does that happen to both the OHs?
That's right. So this is not a balanced equation. There you go. Although, well, I mean, it's tricky because we write it like this. So we had to spit out an extra water molecule, but there are N groups out there that are unknown. So if we want to balance this up, we can put a 2 there. You know, you're not going to get docked tons of points if you don't have a 2, but we did make 2 amides. We made this amide and we made that amide. So formally, we have 2 moles of water that come out of that. Yes.
So the adipic acid and the hexamethyl diamine, are those both monomers, like each of those monomers, and they combine to make a repeat unit?
That's right. So these monomers combine. So you can't take hexamethylene diamine only and make a polymer out of that, as far as we know. You absolutely need to have both the diamine and the adipic acid. Otherwise, you don't get anything. You need them both in there. Good questions. All right. So you can get your clickers out. We're on CD. Oh, geez, I need to start the clicker. Hold on. There we go. All right, yeah, there's something about the power button and then hold down CD so you can handle that. Oh, it's a classic program that runs very slowly. All right. We're back in business here. Okay, so which polymer is correct if we polymerize this dicarboxylic acid and this diol? So remember your functional groups. When we react an acid with an alcohol, what do we get? What's the functional unit called? An ester. And so we're looking for something that looks like an ester. And so this is how you get your eye clickers going. So press an old power button, CD, then it flashes or something. All right, go for it. Which repeat unit is right and which unit gives you polyester? Yeah, I know there's at least 40 of you sitting out there, and so we're going to wait until we get 40. Let's think about A. That's a nice ester, right? That's looking pretty good. What's this functional unit right there? If we connect those two, if we slide it over and connect it, what's oxygen connected to oxygen connected to a carbonyl? Nothing, right? Nothing that we care about. That's not an ester. That's ester. That's looking pretty good, right? And if we slide the repeat unit over, that's another ester, oxygen connected to a carbonyl. That's looking good. That's a possible answer. Let's keep that. Let's remember that. Ester, great. This carbonyl is by itself. If we slide it over, it doesn't have an oxygen. This one doesn't work. And then we have an ester here. We have an ester here. Well, that's looking pretty good. But let's see, 1, 2 carbons between oxygen. We need to remember this funky thing right here. And so if I look, 1, 2, 3 carbons before the oxygen. So even though this is 2 ester groups, and that's all right, someone gave this an extra oxygen compared to the monomer. So that one doesn't work. So the only right answer is B. I know you all got that. I can stop that. All right, we're up to 52. That's great. Yes.
So if D only had 2 carbons, would that also be a correct answer?
That is right. So if D only had 2 carbons, it's okay to put the carbonyls on one side or the other side, and I'll have a slide in that in a second. So you could slide these parentheses around as long as you get the functional groups right and as long as you get every functional group in the right place. Yeah. Oh, geez, I can't even. All right. So this is the question of where do you put the brackets and how do you know that the brackets are correct when you make one of these condensation polymers. And remember, we're on condensation polymers because it spits out a small molecule. And so we talked about where to put the brackets when you have addition polymers. And I'm going to use addition polymer and condensation polymer. And since they're key pieces of nomenclature for this class, you're going to have to know what's what. Addition, you can think of, I just added. It's easy. Condensation, small molecule pops out. I have condensed monomers. And so you have to know the difference between the two. So if we connect a bunch of diacids and diols, we're getting minus water here, minus water here. And we're going to make this polyester. So we made ester here, ester here, ester here, ester here. Where do we put the brackets? And we can use the monomers as a clue as to where to put the brackets. Or all we need to do is just get all of the functional groups and atoms in the repeat unit, and we can write it in whatever order we want. And so first, we find the same exact bond in each repeat unit, and we can put the parentheses there. So we've got both carbonyl groups. We've got both oxygens to make our ester. We have 2 carbons. We're all set. So we can find the bond that repeats, and that gives us a clue where to put the repeat unit. Or we can say, okay, I have my ethylene glycol right here. I've got my terephthalic acid right here, and I just need to watch to make sure that this and this make the functional group I'm looking for. Because remember, the repeat unit, you slide it over. You don't mirror it, so we don't take that repeat unit and flip it over this way and write another oxygen right here, and then write, the carbons and stuff like that. That doesn't fly. Whoops. What we do is, okay, it's connected to a carbonyl. And so we're going to put a carbon there. Carbonyl is going this way. And then let's see, I just have one bond and I'm connected to this ring right there. And then I've got this carbonyl. Then I have an oxygen, et cetera, and I can make my connection that way and put another oxygen here because it's same repeat unit as this. Yep, that makes sense. Okay, sorry I ran out of room there, but this idea that you're taking, in this case, 1, 2, 3 adipic acids and connecting them with ethylene glycols, you get this long oligomer. So we would call this structure here an oligomer, but this whole thing is not the repeat unit because the repeat unit repeats. It's a distinct chemical unit that encompasses everything we need to know about the polymer. So practice this. This is how you practice. And so we can write the repeat unit a number of different ways. And this all flies. So we've got 2 carbons. We have our carbonyls in the right place. In this one, we separated the carbons. That's a tricky one, but we still have our esters in the right place. Make sure the esters are connected correctly to the aromatic ring. I will ask you once in a while, I'll reverse the functional group, and then it's not the same molecule anymore, right? We need to keep our molecule intact. And this is a representation of the repeat unit for this PET or polyethylene terephthalate. Okay, this is probably brand new to everyone in the class if you haven't studied polymers before, so this is going to take a little while to settle. Any questions? Yes.
So will we, if we're like getting everything on the chain or anything like that, will we be expected to write down each, like what we could have variation repeat units, or would that just be too many repeat units for us to actually put down as an answer to this?
So I'll ask you a lot of questions about what are the monomers that make up this repeat unit. So you need to be able to go forward and backward, just like we're going to do for addition polymerization. And you need to know that amide is carboxylic acid plus an amine. Same with polyesters, polycarbonates we're going to get to, things like that. But I won't ask you to draw out like 50 repeat units. Maybe you'll have a homework problem where you need to draw 5 repeat units or something, but that's just busy work, right? Getting it. What I'm really concerned about is making sure that you get all the monomers in there, you get the functional units correct, and you know where to put the parentheses. That's what I'm most concerned about. But I will ask you questions like the clicker question, which one is correct? Or I'll ask you to draw it in different ways. Show me two different representations of the same exact polymer. And so you need to be able to do stuff like this too. But going forwards and backwards from monomer to polymer is important. And that's because there's some commercially available polymers that are addition polymers and some are condensation polymers. So you notice most of them are addition polymers: polystyrene, polypropylene, polyethylene, PVC, but PET is a really important polymer made by condensation. Nylon 6,6, we don't recycle nylon 6,6 right now. That's a really important polymer in the world. And so we need to know what nylon 6,6 looks like. So it's something to become familiar with. Any questions? All right, this addresses exactly a homework problem. And so when I ask you what the molecular weight of the chain is, its degree of polymerization, and this is also X. So sometimes we use N, sometimes we use X, and M0 is the molecular weight of the repeat unit. And so this is for addition polymerization, where we have this definition of the repeat unit. And so sometimes I'll ask you what the molecular weight of the repeat unit is, the M0. Sometimes I'll ask you what the molecular weight of the chain is. And then I'm asking you what capital N is, capital M, sorry. So make sure you can go forwards and backwards. Sometimes I'll tell you that a polystyrene chain has a molecular weight of 10,000 grams per mole. And you need to know that the M0 polystyrene is, whatever it is once you add up all the carbons and hydrogens. And so you're not going to be drawing monomers that have a molecular weight of 10,000 grams per mole, right? Or a repeat unit. And so that gives you a clue. Really high molecular weights are generally chains. Reasonable molecular weights are probably the repeat unit molecular weight. We're going to skip the clicker question because this is the homework question right here. And so if we want to find the average repeat unit molecular weight of this polymer, how do we find the average? Okay, go ahead.
We need to add up each repeat unit.
That's right. So you take the molecular weight of each repeat unit, add it up, but then you need to divide by the different fractions of the repeat unit, or the different mole fractions in this case. So the average repeat unit is the weighted average based on the number of moles. If I told you that X was 10, Y was 15, and Z was 100, you could come up with a weighted average for that. And so even though this looks a little complicated, this is just weighting the different M0s by their mole fraction. And here's an example right here. And so this M bar 0 copolymer, anything with a bar on top is usually an average. So this is M0 of a copolymer, and it's the average between those three monomers. And so this is exactly the homework problem. I give you the weight fraction in the homework, and you need to convert that to mole fraction, because you can't use this formula based on weight fraction because you don't know how many moles there are without doing that calculation. So take a look at that, think about that, and if you can't do the copolymer problem on the homework, come to office hours. The last thing I'll say in the last 5 seconds is that oftentimes molecular weight is a distribution, which means there's lots of chains with different molecular weights. So oftentimes we don't talk about one polymer that's 10,000 grams per mole. We talk about a distribution of molecular weights where there's 8,000 grams per mole, 10,000 grams per mole, 12,000 grams per mole. They're all mixed up, and we'll learn how to handle distributions on Friday. See you then.
Oh.